Por favor, todos tomen asiento para dar inicio a este programa del día de hoy. Buenas tardes. Bienvenidos a la 11ª conferencia Raúl J. Marsal. A continuación, el maestro en ingeniería, Juan de Dios Alemán, dará una breve semblanza del ingeniero Marsal y de nuestro conferencista magistral, el profesor Andy Fourie. Adelante, Juan de Dios.
¿Pueden avanzar, por favor, una? Bueno, gracias a la SMIC por esta invitación. Es un honor para mí estar aquí en la presentación de la semblanza del profesor Marsal y de la conferencia del profesor Andy Fourie. Vamos a hablar muy brevemente de una semblanza del profesor Marsal para aquellos jóvenes que a lo mejor no están tan enterados de la aportación que hizo el profesor Marsal, y enseguida comentaremos también la semblanza del profesor Andy Fourie. Bueno, Raúl Jaime Marsal Córdoba nació en Buenos Aires en 1915 y falleció en Ciudad de México en 1990. Se graduó como ingeniero civil con honores en la Escuela de Ciencias Exactas, Físicas y Naturales de la Universidad de Buenos Aires, y posteriormente fue becado para estudiar un posgrado en el Tecnológico de Massachusetts, en el MIT, donde obtuvo su grado de maestro en ciencias en 1944, bajo la dirección de destacados profesores como el doctor Donald W. Taylor. Después continuó su formación en la Universidad de Harvard, donde trabajó bajo la tutela de Arthur Casagrande, uno de los más influyentes ingenieros de suelos de la época. En 1945, su carrera tomó un rumbo inesperado debido a circunstancias políticas que lo llevaron a establecerse en la Ciudad de México, todo asociado a la Segunda Guerra Mundial, y aquí comenzó su participación en el estudio de hundimiento de la Ciudad de México, tarea que lo posicionó como una figura clave en la geotecnia nacional. Sus estudios sobre el subsuelo del Valle de México permitieron una mejor comprensión de las causas y evolución del hundimiento, aportando criterios fundamentales para la zonificación geotécnica y sísmica de la ciudad y mejorando las normativas de construcción. Durante su carrera en México, el profesor Marsal, o el profe, como le decían sus colaboradores más cercanos, fundó los laboratorios de Ingeniería Civil en la Comisión Federal de Electricidad, lo que generó un profundo impacto en el desarrollo de grandes proyectos de infraestructura. Al integrarme yo en CFE a principios de los 90, tuve la oportunidad de trabajar directamente con todos los equipos que el profesor Marsal había desarrollado en esa época y que ya era parte práctica usual ahí en CFE, en los laboratorios de Ingeniería Civil, su uso para la caracterización de enrocamientos. Y gracias a esos avances que había desarrollado el profesor Marsal sobre el comportamiento de los enrocamientos, fue posible aplicar este conocimiento en pruebas triaxiales y de consolidación en enrocamientos, en cámaras triaxiales gigantes. La cámara triaxial que se manejaba usual en los laboratorios era la de 30 centímetros de diámetro y 70 centímetros de altura, y tenemos un consolidómetro de 1 metro de diámetro y 1 metro de altura para enrocamientos de mayor tamaño. Y utilizando estas cámaras que se diseñó, que fueron diseñadas por el profesor Marsal, se hicieron una serie de diseños de presas muy importantes. Los estudios realizados en esos años, fundamentados en los desarrollos del profesor Marsal, permitió optimizar los diseños importantes de presas como el Cajón y la Yesca, ambas de enrocamiento con cara de concreto y con alturas superiores a los 190 metros. Estas obras de gran relevancia técnica fueron posibles gracias a la visión innovadora y el rigor científico del profesor Marsal. Bueno, ahí estamos viendo una imagen de pues, la época dorada, digamos, de la ingeniería en empresas en México. Vemos allá destacados profesionistas, el profesor Marsal al centro, el profesor Alberro, el doctor Reséndiz, el doctor Covarrubias y el ingeniero Graue, en un evento en esa época, ¿no? El doctor Marsal, lo que tuvo fue que el profesor Marsal creó una escuela en el Instituto de Ingeniería y en CFE con pupilos realmente muy brillantes que lo apoyaron en desarrollar todos los trabajos que realizó, y eso fundamentó muy bien todo el conocimiento de la tecnología mexicana para diseño de presas, ¿no? Además de sus funciones en ingeniería de presas, el profesor Marsal fue pionero en el desarrollo de instrumentación y monitoreo de estas estructuras. Sus investigaciones crearon un acervo de conocimientos que transformó la manera en que se construían y mantenían las presas de colocamiento, facilitando la adopción de técnicas más seguras y eficientes tanto en México como en otros países. La herencia del profesor Marsal en cuanto a la integridad y rigor técnico siguió vigente en áreas técnicas del CFE y el Instituto de Ingeniería, permitiendo a la empresa, en este caso del CFE, desarrollar proyectos de grandes presas con tecnología propia, consolidando así la capacidad técnica de México en este campo. En el aspecto de instrumentación, por ejemplo, se instrumentó la presa de Infiernillo, que es una de las presas que prácticamente, cuando se hacen análisis dinámicos de presas, es la que siempre se toma como referencia porque es la que ha aportado mucha información de este tipo del comportamiento de presas en el mundo, ¿no? El legado del profesor Marsal trasciende no solo en el ámbito de la ciencia y la ingeniería, sino también en la formación de generaciones de ingenieros que han aplicado sus enseñanzas para continuar desarrollando obras de infraestructura fundamentales para el país. Debido a esa aportación, hace ya algunos años se decidió definir e implementar esta conferencia Raúl Marsal en honor del profesor Marsal, y siempre buscando ingenieros de gran prestigio que nos propusieron estas conferencias, y el día de hoy tenemos la fortuna de que el profesor Andy Fourie haya aceptado generosamente estar aquí dando esta conferencia para aportar todavía siguiendo esa herencia del profesor Marsal, aportar conocimiento a toda la comunidad geotécnica mexicana. Voy a hablar una muy breve semblanza del profesor Fourie para enseguida ya darle espacio a su interesante plática. El profesor Andy Fourie es un destacado académico y experto en ingeniería civil y de minas. Actualmente ocupa el puesto de profesor en el Departamento de Ingeniería Civil, Ambiental y de Minas en la Universidad de Western Australia. Sus estudios incluyen una Bachelor of Science con honores, una maestría en ciencias de la Universidad de Witwatersrand en Sudáfrica y un PhD en el Imperial College en la Universidad de Londres. Con una carrera que abarca más de 3 décadas, el profesor Fourie ha centrado sus investigaciones en áreas críticas como la licuación por flujo de residuos mineros, o jales como los llamamos aquí en México, y la caracterización geotécnica de jales filtrados y espesados, y el uso de técnicas electrocinéticas para el desecado y tratamiento in situ de suelos blandos y contaminados. Ha investigado y desarrollado métodos innovadores para la consolidación de jales ultrafinos y el uso de jales como relleno estructural en minas. Andy Fourie ha ocupado diversos puestos académicos, incluyendo roles de profesor visitante en la Universidad de Colorado, la Universidad Católica de Valparaíso en Chile. Ha sido profesor en la Universidad de Witwatersrand y ha desempeñado roles significativos en la Universidad de Queensland y la Universidad de Alberta. Además, ha sido el jefe de la Escuela de Ingeniería Civil, Ambiental y de Minas en la Universidad de Western Australia de 2012 a 2015. Su impacto en la comunidad científica se refleja en su participación en numerosos comités y sociedades profesionales, tales como la Sociedad Geotécnica Australiana, la Sociedad Internacional de Geosintéticos y el Comité Nacional Australiano de Grandes Presas. Ha servido en el consejo editorial de varias revistas internacionales y ha sido invitado a dar conferencias magistrales en conferencias de alto perfil global. El profesor Fourie Ha liderado importantes proyectos de investigación financiados por organizaciones como el Consejo de Investigación de Australia, de BIRS, Billington y la Fundación Nacional de Investigación de Sudáfrica. Estos proyectos abarcan desde la remediación de suelos contaminados hasta el desarrollo de sistemas de cobertura alternativos para las instalaciones de almacenamiento de jales y vertederos de residuos. Su investigación ha contribuido significativamente al entendimiento y desarrollo de técnicas sostenibles en la gestión de residuos mineros. Ha recibido numerosos premios y reconocimientos a lo largo de su carrera, incluyendo la medalla Benjamin Tannenbaum, el premio G.A. Jennings de la Institución Sudafricana de Ingenieros Civiles y el premio Crypto Curie por la mejor ponencia sobre temas de países de desarrollo. Su compromiso con la transferencia de tecnología y el desarrollo profesional se evidencia en la fundación y organización de conferencias internacionales como PACE and Tailings and Mine Closure, los cuales se celebran anualmente en diferentes países. Andy Fourie también ha colaborado en la publicación de guías y manuales de referencia en su campo, destacándose como coeditor de la tercera edición del libro de directrices sobre jales y residuos mineros pesados y como editor asociado de manual de gestión de jales, prácticas líderes del Departamento de Industrias, Recursos y Turismo de Australia. Además, ha sido autor de una guía sobre barreras ingenieriles para jales de uranio para la Agencia Internacional de Energía Atómica. Es un honor, profesor Fourie, contar con su presencia en esta reunión nacional, donde impartirá la 13ª primera conferencia Raúl J. Marsal, cuyo título es Restaurar el equilibrio en el diseño de las instalaciones de almacenamiento de relaves. Su vasta experiencia y conocimiento en la gestión de jales y residuos mineros garantiza que nos ofrecerá una valiosa perspectiva sobre el tema y enriquecerá significativamente este evento. Por favor, recibamos con un aplauso al profesor Fourie. Gracias.
Right, thank you for that introduction. I must say, Friday evening, listening to a foreigner speaking about mine tailings, this is a very impressive turnout. Thank you for coming along. I'll try and speak slowly, because I realize there's some simultaneous translation going on, and I have to always remember to speak slowly. So first up, I think I need to give thanks to Miguel, Secretary of the Mexican Society of Geotechnical Engineering, and of course the chairman, Dr. Ricardo Ortiz, for this kind invitation. When I got the invitation, I was surprised, but pleasantly surprised. I always enjoy the opportunity to talk about mine tailings, having worked in that field for some years now. I did a little bit of reading to get a sense of what the lecture was about, and of course who it is in honor of. And I guess the thing that struck me is that Professor Marsal was obviously extremely hands-on, involved with industry. There's reports of him visiting construction sites and offering his opinion in no small measure about things when they were going wrong. Unfortunately, a lot of academics these days don't get that opportunity, or perhaps don't look for that opportunity. And I think it's, overall we're poorer for that. That integration with academic endeavor and the industry activities is, I think, crucial. And I think that's what came through to me very, very strongly when I was having a look at some of the work he did. And I did manage to read one or two papers of his that I thought were particularly pertinent. So thank you for coming along. Now, I've given it a fairly provocative title, and let's see if it lives up to that. It's an issue that has been bothering me for some time, as I'll kind of explain as we go along, and why this is the case. So, I have an outline there of kind of 5 primary headings. The central one, the brittle behavior of loose tailings, and particularly cohesionless loose tailings, is really the bulk of what I'm going to be talking about. So I'll be spending probably more time on that than most. But I'm not sure if everybody here has a great familiarity with with mine tailings. So I thought a little bit of an introduction might be appropriate. So tailings is essentially the residue that's left over after the mineral of interest has been extracted. Once that's done, when we're dealing with minerals like gold, for example, the amount we extract is absolutely minimal, 1 gram for every 1,000 kilograms of rock that we crush and process. So the rest has to be managed. And the most common way, still today, is to use some kind of slurry deposition system. So the top two pictures there, let's see if I get this to work. That one, the single discharge, and the spigoting system are probably the most common. Tailings is pumped at a very high water content, with solids contents maybe 25 to 45%. On deposition, there's a lot of free water, and the tailings often settle out at a very loose consistency, sometimes even underwater, which is particularly undesirable. Now, there's a lot of talk and a lot of interest in alternative methods, such as high-density thickened tailings that we're seeing in quite a few operations. And of course, everyone is talking about filtered tailings, particularly in places such as Brazil at the moment. And I think sometimes we get carried, or people get carried away with the perceived benefits of some of these technologies. So now we're pumping at a high water content, we're depositing loose, and then we have to construct some kind of impoundment facility. Again, this is not exhaustive, but on the top left, we have a method called the downstream method of construction. The embankment, the shell, the retaining component is built out of usually compacted material. So it's in a generally dense, dilative state. The tailings are stored behind that. And this is the method that's now mandatory in Chile and has been for some time because of the risk of seismic activity. The method we see very, very often in Australia, Southern Africa, parts of Western United States, and many other countries around the world is that upstream method of construction. And here the shell, the perimeter, is actually built sometimes of imported material, but more often than not, built using the tailings itself. And let me illustrate. So we build some kind of starter embankment that's usually with natural material, then fill behind the or behind that perimeter wall, and then use tailings subsequently to continue raising that embankment. One thing I want to point out here is the creation of what is called borrow areas, where we excavate tailings for construction. I'll come back to that a bit later. Now, as you I'm sure no doubt aware, there's been a number of failures of these tailings storage facilities, particularly in recent years. And in 2021, there was a publication looking at an analysis of the statistics that were generated in the aftermath of some of these failures, where a lot of data was gathered about type of structure, volume, height, etc. And what they looked at is what they called they called it stability issues, and I've got an asterisk there because it's not an outright failure necessarily. It's any structure that's undergone some incident or some period perhaps where it wasn't certified as being stable, in inverted commas. So these aren't outright failures necessarily. What it seems to point out is that it can occur with any kind of construction methodology. And the upstream tailings storage facilities don't appear too bad in this kind of plot. However, I think if you dig deep into those statistics, you'll find that generally the catastrophic failures, the ones that have resulted in multiple fatalities, enormous environmental impact, etc., have generally been upstream constructed TSFs. Feijão, Fundão, going right back to Stava, and so on. And going back to one that I have had fairly close involvement with. This was a failure that occurred in South Africa in 1994. Some of you will have no doubt heard about it, the Mary Spruit failure. The dam failed when it was just probably about 30 meters high. It was a gold tailings built using a conventional upstream method of construction. You can see the village that was as little as 300 meters from the perimeter. In that area there, the houses were completely sheared off their foundation level. A little bit about that failure, because I think these are pertinent points, is that it occurred after as little as 50 millimeters of rainfall. It was a short period, but 50 millimeters is hardly a biblical rainfall event. About 500,000 cubic meters of tailings mobilized and flowed for some 3.5 kilometers, and tragically there were 17 fatalities. It occurred 9 o'clock at night. People were at home in their homes, and some of them were even in bed because they were working early shifts. I was working in the field of tailings. I was asked to go down and have a look at the failure, and you can see that entire village was impacted to some extent or another. Very few people kind of escaped the damage. In those days, the whole health and safety thing wasn't nearly as restrictive as it is today, so I was able to walk around, take some photographs and get a sense of what it looked like post-failure. There were also some photographs the following weekend in the newspaper, just showing the impact on individuals. Homes completely destroyed. People, again, would not be allowed today, but going into this tailings, probably containing cyanide in some concentrations to recover their belongings. So when these kind of failures occur, the impacts can be absolutely devastating on communities in particular, and hence the interests in perhaps doing things better. Now, when the post-failure investigations were done, a lot of things came to light which indicated that facility had not been operated anywhere near what was regarded as standard practice, even at that time. For example, the freeboard, that's the allowable water storage, was as little as 15 centimeters. So that's little wonder 50 millimeters caused the failure. It was triggered by overtopping, eroded the embankment, and then the tailings liquefied. So you've got to separate cause and effect. And the tailings then liquefied and flowed, being a very loose material. Now, I make this point here because it really slowed adoption of a better understanding of tailings. The operators and the subcontractors in South Africa who actually build and operate tailings storage facilities, they have been doing this for 90 years using the upstream method. And they said never in their experience had a gold tailings dam, when erosion occurred, exhibited a flow failure. Their prevailing wisdom was that gold tailings are dilative. Now, of course, if you interrogate that just a little bit, the reason they can say that is because they always prepared samples in the laboratory using a fair bit of compaction, so the sample would stand up. And of course it dilated. So they got completely the wrong understanding just because of the method of, I guess, sample preparation, etc. But this was very difficult to push back against at first. We subsequently did carry out some triaxial tests on material from the actual failure. I'll point out two sets of data, isotropically consolidated, then undrained compression tests. And you'll see here that the peak strengths are reached at axial strains of maybe 2, 3, 4%. And then there is some post-peak strength loss. Anisotropically consolidated specimens reach the peak strength at extremely small strains, 0.1, 0.2% strain, and perhaps show some more significant strength loss post-peak. These are the void ratios just prior to shearing. They were all prepared at densities that put them above something we call the critical state line, which I'll mention in a few slides' time. We also managed to get some block samples from adjacent or close to that failed area. and looked at in situ void ratios, and many of them were or appeared to be higher than we could even produce in the laboratory using sample preparation techniques that were current at the time, in fact still are. Some of these numbers down here, I think perhaps the 1.6, 1.8 may be a little fanciful, but nevertheless there were a lot of samples that actually were definitely looser than they would be at what's called the critical state. Now, why is this possible, and why does it kind of contradict with the observations made in the laboratory? Well, I did have a final year thesis student who did some exceptional work, and this is based on an idea Peter Vaughan had many years ago, where he just put a small amount, a really small amount of different clay materials into water and then carried out settling test. So you'll see the void ratio of the series test number 1, that was clean water. Test number 4, that was with bentonite at 14 grams per liter, but even test number 2, with bentonite at a concentration of 1 gram per liter, essentially dirty water, was in fact producing very, very high void ratios. So perhaps one of the things we're missing is that in the TSF, when it's settling underwater, in the decant pond, that water is not clean necessarily. And there's some hindrance that occurs, and we get settlements that are looser. So that was just a bit of an anomaly that I thought was worth mentioning. Okay, so the second topic was static liquefaction, and I'll spend a fairly short amount of time on this. Firstly, what is understood by static liquefaction? Now, there's many definitions. I think this is a fairly simple, almost self-explanatory one. It's a saturated soil mass, so we'll come back to the topic of saturation a bit later. It fails under static loading conditions. This is not liquefaction under seismic loading. It loses its available shear strength and may eventually behave like a dense liquid. The key, I guess, there is that it's under static loading conditions. Now, I guess a lot of people in the field will be very familiar with this, but just in case people here that aren't, a little bit of background is we evaluate susceptibility to liquefaction, and this applies if we're looking at seismic liquefaction as well. But it's all in terms of 2 parameters. It's density, which we represent as a void ratio usually. The higher the void ratio, the lower the density. And some measure of effective stress, usually mean effective stress. And the 2 combined give what's called a state condition. Now, when we do the laboratory testing, which I'll elaborate on a few slides' time, we try and determine when the material is likely to behave in a contractive manner, in other words, would decrease in volume when sheared undrained, or a dilative manner, where it would expand when sheared. And that kind of boundary is that green line, that's the critical state line. So really, essentially, above the line is bad, below the line is good. So if you can compact, as people are envisaging with filtered tailings, you may be able to get into that dilative region. But I think some people have overlooked the question or the possibility that upon increasing height of a filtered stack, you may transition across back into the contractive region. That's a bit of an aside, but I think it's, we need to always bear in mind that we have to keep track of both the density and the mean effective stress. So it appears fairly simple, but it's not that straightforward necessarily to determine this critical state line. A couple of other parameters and definitions that I think are important just to flag here. The first is the slope of the critical state line, or they use the word locus, and that term lambda is the slope of the critical state line, and it's often equated to compressibility. I'll come back to that when I talk about some in situ data. The other one that is very, very common is this parameter shown here, or that psi symbol, so-called state parameter. That is a measure of the void ratio difference between the in situ state, so your current void ratio, and the equivalent state on the critical state line. So it's the difference in void ratio between your existing condition and where you would be on the critical state line at the same mean effective stress. So negative value, as shown there, means you're below the line, dilative, that's good. If you're above the line, it's a positive state parameter, which means the material is likely to be contractive, particularly when, and particularly problematic when sheared undrained. So we'll mention that state parameter a bit later on as well. So how do we get this critical state line? It's usually defined in terms of mean effective stress. I think some of the early work was in terms of vertical effective stress alone, but mean effective stress is now much more common. So we need a test device where we know those principal stresses. The triaxial is the most attractive and widely available. So a couple of good reasons for using the triaxial device. I won't dwell on that last point too much just yet. Now, one of the things that seems to be overlooked at times is that when preparing a specimen to test, to try and determine that critical state condition, and that critical state condition is the end point of the test. It's when, hopefully, pore pressure, excess pore pressure stabilizes, the deviator stress stabilizes, and so on. But samples prepared below that critical state line, such as that, often do not reach the critical state line because, being dense, they start developing shear planes, discrete planes along which the shear occurs. And when you subsequently measure the global void ratio, it's not indicative of the void ratio where the shearing has occurred. And the technique we use, and most laboratories now are using, is to do what's called end of test freezing. So at the end of the test, you freeze the sample, take it out, dry it, and recover all the samples, and you then know the exact amount of water that was in the voids. Being fully saturated, you can work out the void ratio. Otherwise, it is quite common to lose material when disassembling a test. Sample preparation, we still use the method proposed many years ago by Ladd, the under-compaction method, producing the material in layers and then compacting with this little tamping device to prepare loose samples. You then have to subsequently saturate the specimens, monitor volume change, and try and get a sense of where you are. When you start shearing, of course, at the end of the test, you determine that more accurately with the end of test freezing. Okay, so that's how we start doing these tests. But then the question came up, well, how reliably can we measure this critical state line? It was a fairly new concept, probably 7 years ago. So we had a gold tailings we've worked with extensively. We had expressions of interest from a number of laboratories around the world. We sent identical batches, as identical as we could get, to 18 laboratories. We got 16 results. We gave people the opportunity to put their name to their data or to remain anonymous. The only requirement was they had to say that before they saw everybody else's data. So they had to make that call. A couple elected to remain anonymous. Now, a couple of tests we screened out because they'd done really strange things. Some of them had compacted the samples, which, as I've already indicated, almost excluded them automatically. And we screened out all the tests that used the end of test freezing method and then compared the critical state lines. Now, I'll just mention here, just in case you're wondering, the red line was the University of Western Australia line. And I always make the point that that was flagged and distributed quite widely before we got any of the other data, because we were concerned people might think, we fitted our data after the fact. And in fact, it's probably not the best fit in here. The key thing, though, is this point here, that even really good laboratories using similar techniques, and we chose 100 kilopascals just fairly randomly, at that value of mean stress, you're still getting a variation of 0.04. Now we place a huge amount of store on this, the state parameter, how far it is from the critical state line. So I think we should bear in mind that even with good testing techniques, we still have some inherent variation in that CSL. Now I'm sure that variation is going to get less as people get more familiar with the technique, but this showed that up in the study. And then one other final figure I just wanted to show, talking about the topic of static liquefaction, and rather than just in terms of void ratios and mean stress, this is a deviated stress, mean stress plot, isotropic test, and an anisotropically consolidated test. You can see the starting point there. And the point where we get the maximum deviated stress, the maximum Q, a line fitted through that is often termed the instability line. And the point is, you get to that limiting shear stress long before you get to what often referred to as the friction angle line, or the fire-dashed drain friction angle line. You then get a strength loss and potentially get down to some kind of final strength. Many people are interpreting this to be the post-peak strength. I'd try and shy away from the term residual, because I think that applies better to highly plastic clays, but you do get this very low strength at the end, potentially. Okay, so now on to, I guess, the topic I want to spend most of the time on, and that is the brittle behavior of loose and cohesionless tailings. Now, as I said, I did find some of the writings and some of the work from MARSAL to be kind of interesting to compare, I guess. So at the 10th International Conference on Soil Mechanics, that was in Stockholm, in I think it was 1981, there was a general report by MARSAL and also La Rochelle from University of Laval in Canada. Now in those days, I think it's kind of different to many conferences today, in that the general reporters actually did an awful lot of homework in preparing for these conferences. So this general report, I think, was probably 28, 30 pages long. They read the papers in what appears to be quite some detail, and then reported on those, and subsequent discussion took place at the conference. So I think it's something we probably lose a little bit at these international conferences today. So one of the things they kind of passed some comment on, which I took note of, is the question of how to determine the properties of the brittle material. Now, they were referring primarily to clays. In the discussion, and I think one of the papers at that session, there was reference to the Rissa landslide in Norway. I think some of you will be familiar with that. It's a fairly well-studied failure in undergraduate soil mechanics. Very sensitive clay. It failed even though the natural slope was probably 6 or 8 degrees. So they were talking about the Rissa landslide, talking about clay, but I think nevertheless, asking these questions is the kind of questions I think we're still asking today, is how do we identify a brittle material, and to me, more importantly, is how do we characterize these brittle layers, or brittle zones, perhaps. Now, I'm not going to show the video. I'm sure everyone's seen it too many times already. But I think one of the ultimate examples of a very brittle failure was that Fourie or Brumadinho failure, where the failure propagated in seconds. It transitioned from apparently stable to clearly unstable in a very short time. It became very mobile and flowed for some distance. I think one of the interesting things to kind of bear in mind here is that this was probably a full-scale live experiment of stress-controlled loading. Because once the movement occurred, the driving stresses, the governing stresses were still there. which is probably what caused that runaway. It's not like a triaxial test, where we generally load it under constrained displacement or controlled displacement. This is a load-controlled experiment in full scale. Now, that video, I'm not sure if it was deliberate or inadvertent, but it got onto the internet, and of course it went around the world in seconds. And I maintain that that video has completely changed our industry. I believe that if all we had was photographs, like we had at Fundau, and like we had at Mount Polly, etc. If all we had was photographs, I think people would have forgotten about it probably some years ago, largely. Of course, the impact was far worse, with over 270 people killed. But the graphic nature of that video, I think, changed the industry. It also led to the establishment of an investigation led by participated in, I have to be careful with the choice of words, the International Council on Mining and Metals, the United Nations Environment Program, and something called the Principles for Responsible Investing. And they appointed a person out of Switzerland who put together a couple of teams, and they came up with something called the GISTM, the Global Industry Standard on Tailings Management. Again, I imagine people here are pretty familiar with it, but to me that document has had an enormous impact on the mining industry, and a good one. People criticize it, but I think overall it's changed behavior for the good in a very, very significant way. It's got some very profound ideas in it. Now, it has a multitude of requirements and principles. The one I've pulled out here is where they try and deal with brittle tailings. But as you can see, it's not detailed. And I've highlighted a couple of things. It says you need to identify and address. Okay, how? They don't say. With conservative design criteria. How? How conservative? They don't say. And also irrespective or independent of trigger mechanisms. So here what they seem to be saying is what people are often adopting, and that's the philosophies that assume that if it can liquefy, it will, almost ignoring trigger mechanisms. And I think that's probably maybe going too far. But this is, people are very conscious of being compliant with the GISTM. So how do we characterize it? I think we can identify brittle tailings, or at least know that they're there from appropriate CPT cone penetration tests. But how do we then characterize them? And this is something that we're grappling with a lot. So here I've got a couple of data sets. I'll just reproduce the Merry-Sprate anisotropic. You can see peak strength at less than 1% axial strain. We also prepared samples from a slurry of a very uniform bauxite residue. Again, after peak strength, very small strains, there was some strength loss, but I'm not sure that that material is really as brittle as that material. Even if we take Bishop's brittleness index, which is this term here, it's the difference between the peak and residual strength normalized by the peak. They've got similar values, I think you can see. Are they really the same? I'm sorry, this is one of my simple sketches, but let's take a couple of materials, stress strain curves. Material A is this one. Material C is the dashed line. They both have the same peak strength. They both have the same residual strength. So they would have the same brittleness index. I've just noted that if brittleness index is 1, that means it's extremely brittle. It's got no residual strength, just so you know how these numbers work. I showed some of these ideas to a couple of colleagues last week, and somebody pointed out that Bishop also had another index. He called it the rupture index. So I've included that here because I imagine not many people are familiar with it. It's a very obscure publication. So he said, we have a stress strain curve, we have a peak strength, goes down to much lower strength and some residual strength. We've got these two kind of hatched color areas. And he said, let's regard the work done going from peak to perhaps some residual value If there was no strain softening, it would be that square or that rectangle, including both shaded areas. But the actual work is this bottom shaded area. And so to find that there's the E subscript P is the work done if there's no drop in strength. EF is the actual work. And he called the rupture index the ratio between EP minus ER over EP. Sorry, I've used EF and ER interchangeably. I thought I'd change that. And then the reliability index is that ratio. And again, if it's equal to 1, that's extremely brittle. Has no post-peak strength. But again, a limitation with this is that it depends on that amount of strain that you take the test to. Depending on how much further you take it, you'll get different numbers. So it's useful, and in a similar way to Bishop's other index, it's useful, but I was looking for something more. When I was doing that, I came across this some months ago. ICOD, International Commission on Large Dams, have a draft bulletin out. And they're trying to kind of maybe determine differences in brittleness. They're all exhibiting post-peak strength loss, strain softening, and they've got regions they call generally non-brittle, moderately brittle, highly brittle, etc., etc. And I'll point out a couple of points on that. Line C is the Fourie material, tested isotropically, or consolidated isotropically. And then the dashed line is anisotropic. It's this line number D. So you can see really small strain to failure, rapid loss of strength, rapid in terms of strain, whereas the isotropically consolidated specimen is different. Now, they're both exhibiting significant strength loss, but I guess would one be as comfortable with both of them? Is one more of a concern, more likely to lead to a kind of flow failure? So the question we were grappling with is that loss of strength the only indicator then of brittleness? Or should we be looking at something further? And again, going back to work on the sensitive clays, this is a group of researchers out of Norway. They talk about a factor that they call gamma or delta gamma 80. The delta gamma, so being gamma, they're talking about shear strain, but I think it applies to axial strain equally. So this delta gamma 80 is the amount of shear strain going from peak strength, you can see that's the peak, to a loss of 20% of strength. So you're going down to there. So it's the shear strain over which you get 20% strength loss. And I think the kind of the traction for this is that it doesn't depend on how long you shear the sample for. And some tests might go to 10% strain, some to 15% strain. And that distorts perhaps the Bishop indices. Whereas this is focusing on kind of very close loss of strength, the first 20% loss in strength. So we took that a bit further and trying to get something that provided more differentiation, more discrimination, suggested something called, just gave it a name, sensitivity index, or perhaps susceptibility index is another. And trying a few alternatives, this one seemed to give some fairly clear distinctions. That's the Bishop index over the square of that gamma, or the delta gamma 80. So again, I'll show the curves from ICOD, those materials A, B, C, and D, remembering D is the anisotropically consolidated Fourie material. There's the brittleness index according to Bishop, the delta gamma 80, and this sensitivity index. And what appears to be perhaps potentially useful, at least from this, is the extreme difference between those. Now, rather than using subjective terms like generally non-brittle and very brittle, etc., perhaps we can start putting a number, and this suggested sensitivity index may not be ultimately the best, but I think it helps to start discriminating between, for want of a better term, degrees of brittleness. Because I think that's really important when it comes to monitoring, when it comes to perhaps getting some form of advance warning of a failure, etc., etc. Also then went back to the general report by La Rochelle and Marcel, and one of the factors that one of the statements they made, which kind of seemed a little bit out of place from the general discussion at the time, but I think is probably perhaps quite prescient, is that a really important consideration or manifestation is the increasing pore pressure. Now, we often think of increasing pore pressure due to compression loading, but when it comes to contractive materials, it's the increasing pore pressure that results from the shearing action. Because the material is loose, it would tend to densify on shearing if there was volume change allowed. If the pore water pressure is such that drainage is not allowed, there can be no volume change and the pore pressure goes up. And that rate of pore pressure increase could be a really useful indicator as well. And there's a bit of work that was done more than 50 years ago that I think is completely unappreciated. So I'll bring that up here. And this is by Gonzalo Castro in 1969, looking at contractive materials. He did test in a triaxial cell where he could measure the load. He had a load cell in the base of the triaxial. So he carried out tests, undrained tests, 14 minutes to peak, and then 0.18 seconds to complete failure. So once it started failing, unlike a triaxial test, where this test would have taken, to get from peak to residual, would have taken 30, 40, 50 minutes. It took 0.18 seconds. To me, this is much more indicative of the Brumadinho or Feijão failure. It's a stress-controlled loading condition where that runaway generation of excess pore pressure was allowed to occur. And so we're currently running quite a few comparative tests where we can do this kind of test, stress-controlled versus strain-controlled. But there's nothing, it's not at a developed enough stage to share at this stage. Okay, so that's talking about how we test. A lot of the assumption that this is predicated on is that we can recover undisturbed samples from the field. We can take an undisturbed sample of tailings. Can we? This is work published over 40 years ago by a guy called Mohsen Balig, looking at theoretically how you push this a thin-walled tube into a specimen and what the strains are induced as a result. Those different numbers of 40, 20, 10 is a ratio between wall thickness and sample diameter. Now, I know there's additional work being done on this in this field, but I still think it demonstrates a really important point, which is that even with the thinnest walled sampling tube, they were inducing or potentially strains, axial strains of 1%. Remembering the Mary Sprate anisotropically consolidated specimens, by 1%, you've wiped out that brittleness. More recent work by a guy at University of Western Australia carried out some tests in a 1G testing apparatus, pushing in half tubes against a transparent wall, and through the technique of particle image velocimetry, tracking the particle movements. So on the left, you've got a very thin-walled sampling tube. On the right, a much thicker. And from that PIV work, he was able to look at the shear strains that are induced, both within the sample and on the outside. And again, of course, the thicker-walled sample induces greater shear strains. But even the thin-walled sample is producing strains, in this case higher strains, of a magnitude to severely disturb the sample. So that's a little bit of bad news. The act of sampling cohesionless brittle tailings destroys the brittleness that we're trying to characterize. It doesn't mean we may not be able to get the post-peak strength, but it certainly perhaps provides some challenges. Okay, moving on. How do we choose a design strength? And again, something that I thought was perhaps quite pertinent from the work by La Rochelle and Marcel. Again, talking about clays and natural clays, but they advise strongly against using peak strength. Oh, sorry, the authors in the papers advise against using peak strength, and the reporters, La Rochelle and Marcel, strongly agreed and suggested that that should be applied to all kinds of slopes, including natural slopes. And then they said that eliminates the need to do some kind of progressive failure where you use peak and then slowly look at other strength loss. So they were recognizing, the need to come to some sort of strength that wasn't post-peak, but is it the large strain strength? Again, coming back to the GISTM, the question is what design strength to use to satisfy GISTM. Now, rather than adopting a value, and Antonio talked about the operational strength yesterday for clay-like materials. Well, rather than doing that, the norm in industry at the moment is to use what I've called the large strain undrained strength. I don't like the term residual for this. It's usually this little symbol here, undrained strength, normalized by vertical effective stress. So it's a stress ratio term. How do we get that? Well, just do laboratory tests, right? Triaxial tests could get you there. You've got these points down there. But this is assuming, firstly, we can get undisturbed samples, which we can't. Secondly, do we reconstitute them? And when we reconstitute them, what about the fabric or the heterogeneities that might be present? For example, so here's a photograph of a block sample, carefully taken. Here's the size. I've had the sacrificial slide for our United States colleagues in inches. You can see the layering that's evident. And this is very, very common in tailings. It's very unusual to get a completely homogeneous specimen. And what we do see, unfortunately, is when people are determining critical state to compare in situ with reconstituted, they take this material and completely blend it and then do a CSL. Well, it can't be indicative. In fact, it points to another issue. If we have a typical failure surface such as that, if that material is that specimen there, that diagonal line I've just put through there, is the failure surface passing through that sample. It's passing sequentially through those layers, whereas this sample might be passing through this relatively homogeneous layer, which could be really loose and contractive. So we have to be really careful when characterizing these materials. So some people say, well, we may have to do some other kind of test. And before we do that, I just want to point out one other issue is these layers, how extensive are they laterally? In a lot of the analyses we do a plane strain stability analysis, we assume they're continuous. But we see on a lot of tailings storage facilities that borrow area I referred to is very localized. When deposition occurs, again, it's going to fill up that borrow area with super loose tailings. If we put a CPT through there, it's going to give us a very different result than if we did one adjacent. So this lateral variation could be important. Notwithstanding that, if we're trying to characterize material that's going to have a failure surface, going through a distinct layer, perhaps we should be using these direct simple shear tests. Now this is data from the literature. It's peak strength. It's an undrained strength ratio in terms of peak, but it's showing triaxial compression, direct simple shear, triaxial extension. And perhaps that's a way to get the undrained strength ratio for loose cohesionless tailings. However, what we found again and again is that the post-peak strength from DSS tests appears to be very optimistic. And a student has recently submitted his thesis on testing with the hollow cylinder. Ricardo Fanni, one of the most extraordinary experimentalists I've ever worked with. And what he did is he did DSS tests in a conventional direct simple shear device. We used the gold tailings, prepared at a state parameter of 0.12, and we got that behavior, peak, post-peak. Now that would give you a lot of comfort. It's giving you 0.14 strength ratio. You repeated the tests in a hollow cylinder device following a DSS stress path. You got these data. These are the state parameters, all less, i.e. potential, supposedly less contractive than that material, and yet you got much greater post-peak strength loss. Here's a DSS with 0.15. That's showing now perhaps a little more post-peak loss, but not even as much as the hollow cylinder at lower state parameters. So I think it calls into question the use of direct simple shear tests for post-peak. Not for peak. For peak, it's probably still very applicable for getting peak strengths. So when lab testing doesn't work, what do? We go to the field. And the most common method is the cone penetration test. And trying to correlate CPT test data with large strain strengths. Two general categories are often used using failure case studies or correlations with sleeve friction. This is data we reprocessed for a paper about 2 years ago, published by Olsen and Stark, showing liquefied strength ratio against tip resistance. And they had these two dashed lines. I think I'll really draw your attention to is the equation they fit, which has a plus or minus 0.03. Now, if you recall, people are using values of 0.04, 0.05 with an accuracy of 0.03. The tolerance is as much as the absolute. A couple of other things is that a lot of this data wasn't CPT. It was based on SPTs converted to CPTs. And in fact, when you reprocess the data, we actually found a different line. So it's extremely challenging to correlate, obviously, case studies with liquefied strength. Another set of data was published by Jeffries and Bean in their book. They related state parameter to liquefied strength ratio. Here, it depended on the slope of the critical state line, that lambda term. You got different relations. Again, I point out the extreme variation here, or the inherent tolerance that's required. And something that's often advocated, particularly for clay tailings, but I also see it being used for cohesionless tailings, is to use the sleeve friction from an SPT and say that's just your large strain strength. Well, from 2 case studies we found, that would be the 1-to-1 relation, but we got there were correlations where it is 40% above or 50% below, a complete scatter. So field tests are extremely challenging. So a couple of comments I want to make on determining large strain strength. I don't think there's any currently accepted standard laboratory method. And probably the triaxial is better than DSS, but it's still not perhaps the absolute best. In situ tests have a large variation in derived values. And when we're placing so much store on this number, we should be getting better numbers, I think. So what do people do? Well, they go to this lower bound. And one of the large multinational companies in Australia, they just call for the lowest plausible value, which I'm not sure what that means. But that number, and this is really the crux of my talk, is that number is costing the mining industry hundreds of millions of dollars. And it's going to continue to do so. And why is that? Well, the final topic I want to talk about is how to manage these storage facilities. When you do an analysis with a low undrained strength ratio, a factor of safety of 1 or 1.1, usually the only way to deal with it is to construct some kind of stabilizing buttress. So here I've constructed a buttress of waste rock on top of my upstream constructed TSF. It's a counterweight that gives you the additional factor of safety. It's crude, it's effective, but it can be expensive. I use this plot a lot. It's from a couple of people out of Canada, I think. About 4 years ago, they published a paper on a hypothetical TSF, Tailings Storage Facility, obviously based on their project files. And they looked at the cost in millions of dollars per 100 meter of TSF. Solid triangles is the one to focus on. That's using a stabilizing berm, and it's all a function of this liquefied strength. So if we use 0.05, it's 1.5 million. If we use 0.1, it's about 0.8 million, about a factor of 2. And it all hinges on that number. And this is per 100 meter. We're constructing buttresses of 3 or 4 kilometers. If you multiply that by all these millions of dollars, and it's going to be ongoing. Once you start this process, as you raise the TSF, you're going to be raising the buttress. It's costing millions of dollars, and what concerns me is I think it's going to make some mines unprofitable, unoperational. So, quick question is, do upstream TSFs therefore have a future? Well, we seem to have forgotten in many cases some of the basics. ICOLD in 1994 emphasized the need to maintain a partially saturated condition. And a couple of the figures shown here is they have that little sketch where that number 6 is a drain, very permeable drain, which draws down the phreatic surface, creating that zone of partially saturated material. Alternatively, you can construct these drains, number 3, intermediate beach drains. And here's one that we installed recently in Western Australia. That draws down the phreatic surface again, creating an unsaturated region. And what are the benefits of decreasing the degree of saturation and bringing it less than 1 or less than 100%? This is some work a PhD student of ours is currently doing. I point out it's a plot of stress against strain, degree of saturation increasing in that direction. The light colored line is about 97% degree of saturation at almost exactly the same void ratio. With 88% degree of saturation, we get virtually no strain softening, so to speak. We also found many years ago, working with the oil sands tailings, that even below the phreatic surface, and this is an unusual case, there were pockets of bitumen that degraded, formed gas pockets, and that decreased the compressibility of the pore fluid. Measuring the B value, even with degrees of saturation of 94%, you got very low B-bar values, and when tested in triaxial compression, these were samples that had been frozen in situ, cored, and then tested in a laboratory at 4 degrees centigrade. So we thawed the samples under controlled stresses. The undisturbed, unsaturated specimen gave that result. Identical specimens, fully saturated or reconstituted, gave very different results in terms of pore pressure. So the compressibility of the pore fluid is decreasing the kind of, I guess, susceptibility to liquefaction. And very recently, Sandra Karimi and his student published work on the impact of degree of saturation on large strain strength. And now this is for a coarse material, so it's not for all tailings by any means. But they're getting as low as 98, 96% degree of saturation. They're getting no post-peak loss of strength. You have to go right down to virtually fully saturated. Again, we're asking what is the degree of saturation threshold? The answer, as it usually is in geotechnical engineering, it depends. For this material, it's not much. You don't have to desaturate much. And then, if we accept that, how on earth do we measure it? Oh, sorry. This is some work we've done recently using the NMR technique. We've worked with our colleagues in chemical engineering, where we measured volumetric water content using NMR, and then compared it with the exact same sample, actual, simple drying measurements of volumetric water content. That would be the line of equivalence. Well, that's not exact. I think it's pretty good. So we now have the opportunity, and I believe there was a discussion on this yesterday in one of the sessions about installing instruments in the field where we could periodically measure degree of saturation. So perhaps invoking the ICOLD techniques and then measuring it is going to give us some benefit. A couple of other quick points I just want to make. These are tests we did on block samples recovered from operational TSFs. They undergone significant drying, desiccation, and some kind of pseudo overconsolidation. We then tested them in simple shear to get the peak strength. So here we've got the peak undrained strength ratio. At low or relatively low effective stresses, that value was extremely high. As we increased the vertical effective stress, that stress ratio came down until it kind of plateaued. So you're inducing this pseudo overconsolidation effect that's giving you much higher strengths and post-peak strengths as well. So again, by managing the facility better, allowing more drying, perhaps we can alleviate many of these problems. And then finally, and this is something that I think we can reflect on a fair bit. Now these are peak undrained strengths from a CPT. It's interpreted using the NKT approach. This is the adopted strength profile. Aside from the fact that all these solid symbols are vein tests and bore penetrometers, etc., what occurs to me is all this strength is being ignored. These are various CPT profiles along the same side of the TSF, and yet we're adopting this value. Is that a plausible lower bound? Are we completely discarding all these strengths? I think there is a lot of work still to be done there. So to come back to the question, do upstream TSFs have a future? Well, I think if operated properly, if there's a wide beach that is not submerged and it has a low degree of saturation, it doesn't even have to be that low necessarily. If you have operational drainage facilities that remain functional, I think these facilities can remain stable. They do have to be monitored, and that's where the last little point I want to make is that mining companies rely on what they call trigger action response plans, where you monitor certain things, you have criteria against which to judge them, and if the pore pressure or the displacement, whatever, exceeds that value, then you trigger an action. Now, something I've noticed a lot is people making claims that I think are unsubstantiated. Let me give you an example. Here we plotted displacements using satellite data, satellite aperture radar, over time. One of those was the Fourie TSF. And this time, 400 days, is up to failure. So we got the first set of data here, the dashed line. We've got the second set, the two dashed lines on the solid line, and the third set. So which of those would have triggered an advance warning? Which of those caused the failure? But of course, I wouldn't be asking the question if there wasn't a trick to it. But in fact, the middle set of data is Fourie. The bottom data, where there's greater displacement, is the Zalazny Most tailings dam in Poland that's been operated very successfully for decades. So I think insight can be useful if it's coupled with a good understanding of stress-strain behavior. But I guess just a warning, there's people advocating it in places where it doesn't belong. And this is just finally a very, very last slide on the experimental work. We modified, you can see it's a fairly crude modification. We built a direct simple shear device here, so that's sitting in that cabinet, which we could load under stress-controlled conditions, both horizontally and vertically. Prepared a sample at a high state parameter, and then gradually reduced the mean effective stress to trigger failure, and measured the strain. When failure occurred, it happened within seconds. The strain really only started accelerating just prior to the failure. I don't think any monitoring device we have currently would have picked up that failure. Okay, so to make some final conclusions. I think it's clear to everyone involved in the industry that tailings storage facilities now are a real point of pain and discomfort for the mining industry in the aftermath, particularly of Fourie. We focus on brittle tailings, quite rightly, but I'd also just flag, people sometimes lose sight of the foundation conditions. As the TSF goes higher and higher and higher, the foundation soils could transition from over-consolidated to normally consolidated. And they could be the source or the location for the failure. Although we can, I believe, identify brittle tailings quite well through CPT tests, perhaps bore penetrometers, we can identify that kind of where they are. Characterizing them as well, I think, is not as well advanced. And then finally, I just think these values where we adopt uniformly laterally, uniformly vertically, for the entire tailings profile, extremely low large strain strengths. I really think that requires closer interrogation because it is costing an exorbitant amount of money. Now, I will be the first to admit that nobody wants to be a consulting engineer to be the first to say, I'm going to double the undrained strength ratio without being very secure that it is reasonable. But I think there's a lot of scope for investigating this issue. Otherwise, we're just faced with the option of going for the lowest common denominator, the lowest plausible value, and spending tens of millions of dollars on stabilizing buttresses. Now, the work wouldn't have been possible without my colleagues, postdoc and PhD students that worked on this project, and funding aside from the Australian Research Commission, we had quite a lot of matching funding from various industry partners. So those of you who've read some of his work, that's Dave Reed. And in front of him is the master magician in the laboratory, Ricardo Fanni. I've drawn on the work we've done together for quite a few of the figures in this particular paper. So I think I probably went a minute over time, so I'll stop there. Thank you.
Muchas gracias, doctor Andy Fourie, por esa grandiosa presentación. A continuación, el doctor Ricardo Ortiz, presidente de la Sociedad Mexicana de Ingeniería Geotécnica, le hará entrega al doctor Andy Fourie de un reconocimiento por haber impartido la 11ª conferencia Raúl J. Marsal. Además, va a todos los conferencistas magistrales de nuestras conferencias principales, se les ha entregado una medalla, pero no hemos dicho qué significa esa medalla. Es una moneda trimetálica, la cual condensa la grandeza de la cultura maya. La pirámide de Kukulcán, emblema de la arquitectura maya, cuyo nombre se traduce como serpiente emplumada, se muestra en su esplendor dentro del núcleo de la medalla. Esta imagen representa la grandeza y sofisticación de su ciencia enmarcada en 2 anillos, uno de ellos con glifos mayas. Al reverso se presenta un elemento nuclear, que es el aro del significativo juego de la pelota, que a su vez hace la alegoría de la cosmovisión maya. La numeración que rodea este elemento hace un tributo al avanzado pensamiento matemático de dicha cultura. La zona arqueológica de Chichén Itzá, declarada en 1988 como Patrimonio de la Humanidad y en 2007 como Maravilla del Mundo, es la representación en esta moneda y que es un orgullo para México. Doctor.
Professor Andy Fourie, thanks to be here. Thanks to accept our invitation. Welcome to Mexico. I will read your recognition. La Sociedad Mexicana de Ingeniería Geotécnica C otorga el presente reconocimiento al Dr. Andy Fourie por su distinguida participación como conferencista magistral de la 11ª conferencia Raúl J. Marsal Córdoba, Restoring Equilibrium to the Design of Tailings Storage Facilities. Thanks, Professor Fourie. Thanks for And also, we want to give you a medal for Presidenta Maya Corpo.
En el año 2004 se creó Sísmica de Suelos. Hoy, nuestra meta es ser la mejor empresa mexicana en el desarrollo de proyectos integrales, geotécnicos, geofísicos y geosísmicos. Grupo de Geotecnia.
Bueno, algunos anuncios. La cena de gala se llevará a cabo a las 9 de la noche en este mismo recinto, por lo cual pues tendremos un receso largo hasta esa hora. Mañana reanudamos las actividades a las 9 de la mañana. Los espero también en el Salón México 2 con nuestra, bueno, en este mismo recinto, con dos actividades, una la sesión comercial y la otra nuestros diálogos de inclusión y diversidad, a los cuales están todos cordialmente invitados y que tendremos pues panelistas muy interesantes, ¿no?, para este tema que queremos pues, compartirles a todos. Muchísimas gracias y nos vemos a las 9.